actually is corresponding to the nth value of x. So x nt is the nth, small nth value of x, and that's multiplied by e to the power j omega naught, that value of x t, and then omega naught, k of course corresponds to this k over here. That's the kth value of this. So k doesn't change, right? So we keep sort of e to the jk omega naught is constant if you think about it, and then we're multiplying by e to the power nt, where n goes from 0 to n minus 1. That's the definition of the discrete Fourier transform, discrete DFT, and then the inverse transform is given by x nt equals t sigma k equals 1 to n minus 1. And that's capital X jk omega naught, because that's your transform value, e to the j k omega naught and t. Again, we take the positive exponential, we multiply that by the Fourier value, and we're going to go, so d omega, we're doing summation over k, and that's the same equivalent as d, it'll become d omega in the continuous domain. Here we do summation over k rather than over n, and so that's the inverse transform. Okay. So the way to understand this, at least that I find like it makes it easier to understand, is that we actually, this tells us one coefficient, okay, one coefficient, the kth coefficient of the transform, and each coefficient is obtained by a sum of the x value multiplied by this complex exponential. So this are the sort of basis functions. We're going to add them up, and that tells us what the kth value is. So we have to do this for each different value of k, okay, because that's what the transform is. So for each, and in some sense, we are computing the this value over here. The amplitude over here is the value of the transform. These are the transform values, and that's going to be given by x k omega naught. Okay, intuitively, that's what we're doing over here. Okay, any questions about this over here? Yeah. Okay, so I think it may be easier to understand this with an example, and so I'm going to do the homework problem here to hopefully to make things a bit clearer. Okay, so what we have over here is a discrete function of time, and the values are x 0t, I guess, equals 1, x 1 equals 1, x 2t equals 4. Okay, it's just a square, so it's 9, 4t equals 16, 5t equals 25. I think that's what I had. So we have t equals 1, right, because I just said the value is 0 to 5, and then t naught equals 6, because this is n minus 1, sorry, this is n minus 1t by definition. Okay, so n equals, this implies n equals 6. And so omega naught is given by 2 pi over 6, which is pi over 3. So that's your base frequency, is pi over 3 radians per second. Okay, and so the first coefficient, and we can do the first coefficient basically by knowing, and as I mentioned earlier, the first Fourier value is always given by the average. Okay, that's a quote unquote DC value. So what we're saying is that, intuitively, we have some continuous value over here. This is the average. That is always going to be the first coefficient in the transform domain. So in this case, the first coefficient is going to be given by 1 over 6 sigma xi, and this is just going to be 56 over 6, whatever that is. Okay, that's the first Fourier coefficient. That's going to be capital X, okay, j 1, okay, omega naught equals 56 by 6. And then x j 2 omega naught, okay, which is the value corresponding to this, is going to be what? 1 over 6, and we have over here 1 times e to the minus j pi by 3 plus 1 e to the minus j 2 pi by 3 plus 4 e to the minus j 4 pi by 3 plus 9, sorry, 3 pi by 3 plus 9 e to the minus j 4 pi by 3. Am I doing this right? I think so. 4, yeah, 9. And so, beg your pardon? I think, yeah, because, let me see, j to pi by, right, I think this is, yeah, plus whatever, it goes up to 16 and 25, and this is basically the value. Now, you may say, what does this correspond to? The way you can correspond, you can expand each of these as cos pi by 3 plus j sine pi by 3, cos pi by 3, j sine pi by 2 pi by 3, etc. And so that will give you some real and some imaginary number. You all look confused, so maybe I made a mistake here. Yes?
For the first term, shouldn't it start with 0? So e to the...
Is it, let me see, but n equals 0.
No, k equals 0.
Sorry, k no, we always, the summation for the transform is over n.
So for the first time, n is 0?
Yeah, n is 0,
So
that's right. Oh, that's right, e to the, that will be 1, I'm sorry, yeah.
Next one is...
Yeah, I'm sorry, that's right, yeah, so that's going to be, yeah, sorry, yeah. 1 plus a, sorry, yeah, that's better, because as I was writing it, I was thinking this doesn't look right to me. Okay, because you need to have those numbers match up. Okay.
And the example
is also wrong then.
Yeah.
Right. I'll fix that. Sorry. Okay, the example is wrong. Okay. Beg your pardon?
X0 equals 0.
Yeah, it should be 0. X0. No, it's the first value. In the summation should be 1/9, 1 plus 1 plus. Yeah, it is a 1 plus term missing over there, or 0. Or actually, I take it back. Oh, x0 equals 0. That's why actually it is correct. Yeah. Okay. It's only. Yeah, and so I take it back. In the example, x0 was 0. In example in the text, x0 was 0. So I skipped the term because we had x0 here. X0 equals 1. In the example, x0 was 0. So that's why I skipped the first term. So this one actually is correct. I hate having to think when I'm teaching. Okay. Okay, I don't know how to fix that. That's okay. All right. Yeah.
So in the 56 by 6,
Yeah.
you say k equals 1, right?
Beg your pardon. K equals k equals 0. Actually, it should be x0. I'm sorry, yeah. What am I doing here? Give me a second here.
That's some example.
The example is correct in the book, yes. I'm just saying over here, I'm just thinking whether it should be x1 or x0. Let me try and go.
Only when you have k equals 0, you lose the exponential.
Right, you do. You only when k equals 0. So this should be x0.
And
This should be x, yeah, xj omega naught. Yeah, you're right. This is x1. So this is xj1 omega naught. So honestly speaking, this is pretty confusing even for me. Okay, I can never keep this straight. I hate things like this. I rather work with. I'm not a mathematician. Okay, I like to build. I like to write code. Actually, I don't like to do this stuff. So I have to force myself to do this, and so I always end up making these off by one mistakes and trying to keep track of things. So I'm the perfect person to teach it to you because I'm also kind of working hard to understand this stuff. Okay, but the example is correct, thank goodness, and actually this solution is also correct. So that's good. Okay, thank you. Yes.
we can leave this in this form, right?
Yes, you can. Yeah, I mean it's plus 9, whatever. Yeah, I mean I just want you to realize that this is not some magic. This is just a complex number. It's going to end up being basically something a plus jb form, where we compute each of those. It's not a big deal to compute it. Okay, just use the Euler formula, you can compute it. Okay, it gives us some complex value, right? The transform value is a complex value, it's not a real value. Okay, that's why we have the j, it's indicating to us that we have a complex value over here. Okay, any question? That t-shirt, math is fun, is not for today. Okay. All right, I'm going to move on to the next one, the FFT, because actually I'm a little bit running over time, and I do want to tell you this short story though, because I do want to change your brain a little bit. So I'm just going to tell you about how to make money while doing good science. And the person who exemplified this is a guy called J.J. Thompson. So how many of you people have heard of J.J. Thompson? You can, it's okay, you can leave it on, it's all right. How many people have heard of J.J. Thompson? One, raise your hand. 1, 2, that's all. So we're actually pretty much indebted to J.J. Thompson for a very, very important invention. Okay, so how many people know, so do you know which one it is? What did he invent? Not exactly. Well, I guess he did that too, but the refrigerator, the fridge comes from the Kelvin effect, and J.J. Thompson is the name. He became Lord Kelvin later on. And if you ever seen a fridge called the Kelvinator is actually named after Lord Kelvin. So he was a physicist in a lab in Edinburgh, Glasgow, somewhere in Scotland. And he was a very, very good physicist. He actually came up with the fact that when you take a tube and you blow air through it and you put your hand over here, it'll actually feel cool. So evaporative cooling. So if you have a vessel and you have a small hole and the air is coming out, it'll actually cool, and that's how your fridge works. You have a Freon or some refrigerant, and you put pressure and expands, and the expansion actually cools it down, and that's without refrigeration. Basically, you couldn't keep food fresh. Okay? It's a very different world when you don't have refrigeration. Anyway, but he got asked to solve a different problem. He was asked to solve a communication problem, and the communication problem was this. Morse and others have figured out how to send telegraph signals over a long wire. Okay, they have very long wires. In fact, they have wires connecting New York and Boston and all the way to Chicago and so on. And they were sending signals, and they say, hey, let's put a wire across the Atlantic. Okay? And they did. They put a wire across the Atlantic. And the big problem they had actually was that sharks would keep biting it. The sharks, for some reason, would snap wires. Even today, they do that. So the wires that go across the Atlantic, they used to use tar in the beginning. Now they use steel. It's actually a big bundle of steel sheathing, and then inside they have other steel sheathing, and then right now they use optical fibers. In those days, they use copper. And they sent it across. They sent these big ships across, and they managed to get the wire across. But the signal coming the other end was very weak. It was so weak that we couldn't detect it. And the people who did this weren't physicists; they were engineers. They just put it in, and at the other end, they said, "Oh, we're going to make a lot of money sending this." In fact, they're making no money because the signals are too corrupted. So they said, "Who's somebody who can fix it?" And they picked Thompson because he was one of the smartest guys around. They said, look, help us figure it out, can you send this information? So what Thompson did was he invented what's called the Mirror Galvanometer. So how many people have heard of the Mirror Galvanometer, or maybe even used one? Raymond is the only exception here. So what it is that we have essentially a coil which is connected across the Atlantic, and going through this, you can think of this as suspended inside the coil is a very fine fiber with a magnet on it, and the magnet is a small mirror, okay? And you shine a beam of light on the mirror. And what happens is that when the coil is energized, the magnet twists a little bit, ever so slightly, okay? Just slightly twists. But that is enough for the beam of light to be moved, okay? So it's exquisitely sensitive, okay? And in fact, this fabric is actually human hair. It turns out to be the most torsion. It restores itself after a small torque. And so you put this over here through the middle, and you put the magnet here and put a beam of light, and you shine light from a candle or something, I guess, because they didn't have electric lights in those days. Or maybe they did, I don't know. At any rate, every time somebody would press a key in New York, the thing would go a little bit. And so they had actually young men sitting there just watching this light. Okay, and they would note down, the Morse code based on these things, and it worked. So the signal, which was extraordinarily weak because they didn't have amplifiers, nothing, just sending a signal across with as much power as they could, went 2,000-3,000 kilometers, maybe 4,000. I don't know what the distance was, but it was able to work, and so they made a lot of money after all, because they could have these guys read these signals using the Mirror Galvanometer, which he invented, and they gave him quite a bit of money. And he became very rich. He actually owned his own yacht, and he went around doing scientific experiments in his own yacht, and he became a partner in this company called Cable and Wireless, which I think I mentioned to you last time. Cable and Wireless is still in existence, I believe, and one of the largest companies doing wireless, well, in this case, they do fiber optic communications across the Atlantic, Pacific, whatever is still around. So mainly all because of this sort of invention that he had, and it must have been around 1870 or so. And this was all before wireless. Of course, when Marconi came with wireless, this became obsolete, right? And at least for some things it became obsolete. Though we still have transatlantic cables, but they're for fiber optics. And we actually lay these cables down in shark-proof cables. If you ever go to the United States and you're driving on I-95, which is this freeway that goes along the east coast of the US, and you go south from towards Philadelphia, south of Philadelphia towards Baltimore, and at the Baltimore harbor on the left-hand side, you might see, if you're careful, you'll see a ship, and on the ship it'll be labeled TAT, and it'll probably be up to 11 or 12, I think. TAT is transatlantic cable ship, and it's actually a ship with big spool of cable on top. That's what they use for laying cables. And I used to live near there, and every once in a while I would see that ship docked over there. And that was a transatlantic cable ship, which was used to lay those cables. Okay, so that's enough story, and now I can get back to this. Okay. Okay. Right. So the fast Fourier transform is actually nothing more than a hack. Okay. It's basically just a quick and dirty way of computing the discrete Fourier transform. And honestly, when I first saw it, I was underwhelmed and like, why are people so? It's such a, what's the big deal? It's really nothing at all. The problem is that, as I see it, the fast Fourier transform was invented by non-computer scientists, so they thought they were being super smart. But all they did was just, trivial recursion. If you studied this you would study this in sort of 101, whatever, the 130 over here or 125, whatever. It'll be the first thing you study would be in computer science would be, we're just going to use recursion. But for the people who did it, I guess the physicists and the engineers, they were super impressed with themselves and they gave it a separate name, fast Fourier transform. I'll show you what it is and you'll see it's really nothing at all. So the first thing they did was they said this notation is too awful, which I completely agree. So let's take this notation and simplify it. And the way to simplify it is, let me forget about the inverse right now. I'm just going to expand this term. So we want xk, xjk omega naught, the kth term, is going to be given by 1 over nt, right? So what's that going to be? So it's going to be x 0, okay, e to the, so it's just going to be x0 actually. Plus x1, small x, 1 or xt, because it's 1t, e to the minus, let me just write this down properly. I guess I didn't do that, so it's j1 omega naught, jk omega naught 1t, right, plus x 2t e to the minus j k omega naught 2t plus and so on, right? And then this until the n minus 1th term. I'm just expanding this out. Now I'm going to put some simplifications down. So let's assume that t equals 1. Okay, so we just arbitrarily say sampling period is 1. Whatever it is, we'll just make it unit. And second, we'll say that t naught equals nt, which is going to be n. So that's by definition, we get t naught equals n. Then omega naught is going to be 2 pi by t naught is going to be 2 pi by n by definition. And then finally, we'll say that, which implies that e to the power j we'll say e to the power j k omega naught is going to be e to the power j 2 pi by n times k, right? And we'll write this as omega n to the power k. So we'll just write it like that. So we'll just say that e to the j, this thing over here, e to the j 2 pi by n, which is essentially some constant complex frequency, we'll call that as omega n. So if using my other color here, let's say that this piece over here is going to be this piece over there, okay? So if we do that, then this mess over here becomes much easier to understand. We are saying that we'll say that xk, and in my notes there's in the text there's a mistake, so I corrected that. So it's not xn, it's xk is going to be given by 1 over n because t disappears. It's just going to be x0 plus x1 omega n to the minus k, because the j omega naught t, all of those go away, right? Because t is 1 plus x2 omega n to the minus 2k plus and so on. So all I've done over here is those things in yellow. I've made t equal 1, t naught equal n, omega naught, well, if t is 1, omega naught becomes just 2 pi by n, and then I replace this j 2 pi by n with omega n, so the e sort of goes away. And now this looks a lot cleaner. It's the same thing. We haven't really changed anything. All we've done is to simplify it and say that xk, the k term is 1 over n x0 plus x1 omega n to the minus k, omega n to the minus 2k, etc. Okay, so any questions about this so far? Okay, so this is where people are saying, oh, this is complicated. Why? Because omega n is a complex quantity. It's e to the power j2 pi by n, and what I need to do is for each value of k, I need to compute basically n values of omega, or powers of omega, omega n to the minus k, minus 2k, minus 3k, minus 4k, all the way up to omega minus n minus 1k, right? And it's a lot of powers of omega. And again, remember this was being done in the days when there were no computers, right? You had to do it by hand, and computing the powers of a complex quantity, when you have to do it for, let's say 1,000 or 1,000,000 elements, right? It's a pain in the neck. So they say, can we get around that? Because we don't want to compute powers of complex quantity. And the fast Fourier transform is really nothing more than doing this in a clever way. So to show what the fast Fourier transform is doing, I'm going to do an example where I am going to assume that n is a power of 2, actually n equals 8. If it's not a power of 2, it can still be done, and it's a bit messier, but let's assume it's a power of 2. And again, in practice, in all cases that I've seen, we always use a power of 2. It just makes life much easier. We'll just use a power of 2, and you'll see why we need a power of 2 in just a moment. So in other words, the number of samples which is taken will be this, in a duration will be some power of 2. Okay. Once we do this, then we had essentially simplified this expression over here. Okay, so let's do this expression, but we'll assume n equals 8. And then what is going to be the case is that, actually I'm doing it for n equal, oh, let's see, so n is even. Okay, sorry. The homework, let's say n is even, so we don't even need a power of 2 for right now. Okay, so we're going to write this as 1 over n. Okay, let me just use the colors here because it will make life easier. I'm going to write this as x0 plus let's write this one as x1 omega to the minus k, omega n to the minus k. In fact, I'm going to skip the n just to make it life, so you don't even need the n. So omega minus k plus x2 omega to the minus 2k plus x3 omega to the minus 3k plus and so on, plus n minus 2 omega to the minus k times n minus 2 And then the last term is going to be omega, okay, omega, sorry, x n minus 1, omega to the minus k n minus 1. Okay. So what I've done is to just write each term in a different color. And what I'm going to do is to show that these two even and odd terms can actually be made to look like each other. Okay. And how do we do that? Let's look at these white terms, x0, x2, and so on until this one over here. And actually just focus on the powers of omega over here. This is omega to the 0, minus 1, minus 2, minus 3, and so on. So I can write this as the following thing. I can write this 1 over n. And this is, let's say that omega e equals omega squared. Okay. That's simplification I'm going to make. So then these are all powers of 2. So this just becomes omega e to the power k, omega e to the power n minus 2, sorry, n minus 1. So let me just write this one over here. So x0 plus x2 omega e to the minus k plus x4 omega e to the minus 2k plus, and the last term is going to be x n minus 2 omega e to the power k n minus 2 over 2. Okay, and this is just replacing this one thing over here. And then the yellow terms I can rewrite in the following way as, I'm just going to rewrite this in one step instead of following this over here. It's going to be omega to the minus k over n plus x1 plus x3 omega e to the minus k plus x5 omega e to the minus 2k plus x n minus 1 omega e k. Okay, and the reason is because when I multiply omega minus k with this is basically omega to the power minus 2k, I get minus 3k. Okay, so this 3 becomes 2 plus 1, and so on, 5 becomes 4 plus 1, etc. So, and now this over here, okay, is using only powers of omega e. Okay, it's using minus e, 2k, etc. up to this one over here. Right? So if I were to just use an example with n equals 8, the powers of omega, you can just write the powers. The powers of omega I need are basically 1, 2, 3, 4, all the way up to, let's say, 7. I'm going to split that up as 2, 0, 2, 4, 6, and then 1 times 0, 2, 4, 6, in which case I'll get, 1, 3, 5, 7, and I get 2, 4, 6, and then these two look the same, right? Do you see what's going on? And any questions about this over here? So now what we see here is that we have over here two summations, both of which have half the number of terms because we have k times n minus 2 over 2. It's basically half. Okay? And so we can recurse. We can just say, okay, these guys I'm just going to break up into even and odd. These guys will break even and odd. When I break it up into even and odd, what will happen is that I'll have omega e to the power 2k, 4k, 6k pulled out, and it's just recursion, right? And so in the end, all we need to do is to compute omega square, omega to the 4, etc. And then we just multiply it each time with just omega to the minus k each time out, right? And we'll get all the even and odd terms. Okay, and that's fast Fourier transform. Why is it fast? Because we don't need to compute these powers of omega. We just need to compute a certain number of powers of omega. How many powers do you need to compute? Well, let's just think about that. If you have, let's say, in the homework example, it was 0 to 31t was the range, which means I had 32 values, right? Because this is n minus 1. So the omega, so n equals 32. If n equals 32, how many powers do I need? Well, if you think about it, you need to compute basically omega. We need to compute omega square, omega to the 4, omega to the 8, omega to the 16, omega to the 32, right? And this is omega to the 1. So we only need to compute these 4 values, okay? And so we only 4 powers to compute, and that's the answer. We need to compute only 4. Am I missing something?
No, I don't need 32.
You don't need 32. Why do you not need? Why do you not need 32? Oh, because let me see. And give me a second here. So we need to have omega. Well, it depends on the last step. If you're going to compute the, we need omega to 32, right? Because it's.
I think we only go up to
We need a 31. Oh, right. Okay, so 31 is going to be written as. Okay, yeah. Because you're going to write 31 as 30 omega to the 31 will be written as omega times omega, right? Square times omega to the 4 times omega to the 8. So omega to the 16, so 24, 28. So yeah, that's right. So we just need 2, 4, 8, 16. That's the highest power that we need to compute. So basically, yeah, we need only the values of yeah. So we need 1, 2, 4 values.
But we still need to calculate omega of n as well. So it's 5 factors.
We need to, yeah, but we need the powers. I said how many powers of omega do we need to compute? I think that's what I asked for, right? So we need to compute 4 powers. Omega is the basic thing, so the answer is 4, right? Yeah.
If you ask how many powers of exponential we have to compute.
Right. Okay, as long as if you say, okay, these are the powers, right? Square 4, these are the 4 powers that you need.
Yeah, but the first one is technically still a power of exponential.
Yes, if that's what you think,
Yeah.
it's correct. Again, what I want you to do is to focus on the big picture here, right? Don't get caught up in the details. The big picture is we have logarithmic number of things. I always get confused on the off by 1. So here again, it's the same thing. And so, what's the big picture? Let's say we have 16,000, powers to compute. Why? Because we're doing 16,000 samples, which is not unusual, by the way. You can certainly do 16,000 samples. 16,000 is 2 to the 10, so it's 14 to the power 4. It's 16,000 is 2 to the power 14, right? 16,000 is 2 to the power 14. 16k is 2 to the 14, and so we only need to compute 14 powers of omega, or 13, okay, or 15, I don't know. 14 plus minus 1, okay, as opposed to 16,000 values, okay. That's a big deal. That's a big deal, right? So that's why it's fast. If you had to compute 16,000 powers of omega, it doesn't matter whether I'm computing 16 or 14 or 13, okay? It's a lot faster than doing it. And so this is really, really important from that perspective. Okay, this is the power of a logarithm in some sense. And this is why we use DCT or DFT everywhere we want to do a transform. Okay, we want to transform, we take a time series, okay, we say it's time limited, we choose the sampling numbers, let's say it's some power of 2, like 2 to the 14. We just need 14 computations of this, and then we can just, it's all multiplications and additions. That's it. And that's why we say fast Fourier transform is fast. So it's way faster than computing that. And that's why it's used everywhere. Okay. And so when you take a digital picture, with your cell phone or whatever, that's using DFT, DCT, and all your digital TV, it's all using that as well. So yeah, so it's a big deal. Okay, any questions about this? Okay. So in the case of I should add that in the case of the CD, we are actually doing time sampling. Okay, we're doing time sampling. In the case of JPEG, we're actually sending Fourier coefficients. Okay, the difference. In the case of JPEG, if you open a JPEG file, look at the numbers inside, those numbers are not samples. Those numbers are actually the Fourier coefficients that are being sent, which is why we have the blocking effect and so on. Okay. Whereas in the case of a CD, we're doing time sampling, but we're using the same theory. In one case, we're saying how fast should we send time samples. The other case is saying, how many coefficients, what the coefficient value should be. Here we're sending these are the coefficient values. You can compute these, we're sending the coefficient values. Okay, so those are very different things that are being sent over here. Okay, I think that's all I wanted to say about the discrete Fourier transform, and that leaves me just a few minutes to talk about Z transform. So I'll start with that, and then I guess I'll finish it after on Friday. Let me just begin talking about the Z transform. Okay, so I'm going to leave this up. So in the DFT, we basically have a time limited discrete signal. Okay, and so we can generalize it. We can say what happens if it's unlimited. Okay, so we don't have it to be unlimited. And so and then instead of doing and it's still going to be discrete though, we're going to keep it discrete because we're going to unlimited. In that case, we get basically the Z or the Z transform. And the Z transform is still in discrete quantities, okay? But the nice thing about it is that the representation is a lot easier to work with, because instead of using complex exponential, instead of using the e to the j omega form, we'll use the a plus jb form, okay? And we'll call this as the complex variable z, okay, or z. And when we do this, it turns out that many of the notations become a bit easier. And so the preferred transform for dealing with discrete quantities when you're trying to do analysis is actually the Z transform. We rarely use the discrete Fourier that I showed about earlier. And the reason is because not only is the notation easier, it's also because the discrete Fourier has the same problem as the regular Fourier transform, which is that it's not defined necessarily. Okay, it's not defined because it may not converge, right? We're not guaranteed that these things are going to. If it's time limited, etc., then it doesn't matter. But when you have a infinite sequence, we can't guarantee convergence. The Z, in that sense, is like the Laplace. So you can force the value to converge by pre-multiplying with an extra value, which is the Z value over here. Okay. So to be more precise, we are talking about a signal. So we're going to talk about the signal xk. So all this complex notation basically disappears with the Z transform. So here we are just a signal xk. So that's your signal. So now we've even given up on the sampling. We're not talking about nt. We're just saying we don't care where it's coming from. It's just some discrete signal xk. And then the transform is given by the Z transform. We call that x of say, and x that is given by sigma k equals 0 to infinity. So we don't even want to go. We're only talking about causal signals. Xk z to the minus k, and that's it. It's really as simple as that. And now we get back to the heart of what the transform domain is doing, right? If you remember the Fourier series, we kind of are looking at ck, some coefficient ck multiplied by some exponential. Here, the exponential form has been replaced by the a plus jb form, the z over here. And we are just doing a summation, okay, because it's in this case because it's discrete, okay. We don't really have continuous. We can't do dt or something. There isn't any dt. It's going to be a summation, and we're assuming that x k equals 0 for k less than 0, except for the homework assignment where I was looking at time reversal, and anyway, so we'll come to that probably in the next class. I want to just write down this form over here, and in the next few minutes I'm going to give you some intuition of what's going on. So what we're doing here is to say that we have some time series xk, okay, so that's some time series, and so now we know that it looks like this, and we ignore anything before k equals 0. So this one is going to be k. This is xk. Okay, great. This xk may or may not converge. Okay, may or may not converge because it could be some value. For example, if it's just a unit, right, it's going to not converge. Every time you add k equals, its value is infinite, right? It's going to be infinite. However, when we multiply it with the helper variable z, this, if it's large enough, or okay, is going to force the value of this sum to get reduced, to converge, and this has the same role as e to the minus sigma that we used in the Laplace transform. In the Laplace transform we were trying to compute the transform, but we couldn't make it converge, so we multiplied by the e to the minus sigma. It's exponentially declining. So in the z, because we have this and we have this a to the jb, so in the case of Laplace we're kind of looking at the sigma being in the left half of the complex plane. Here what we'll have instead is that z has to be larger than some absolute value. So this is a real value, this is imaginary. And we're saying if z is larger than some magnitude, as long as it's big enough, then it's going to make this converge. And so x is the transform value is a function of what value you pick. If you pick this value over here, you get some value over here, some value of the sum. If you pick that value, it's some value of the sum. So it's a function of z, and that's why we have x of z over here, and it's just this product over here. Okay. Now the nice thing is that even though it's a very simple transform, it actually has all the properties that we care about. Very, very interesting properties. That is, for example, linearity, it has time scaling, time shifting, and most importantly, convolution. So multiplications in the convolutions in the time domain become multiplications in the transform domain. So if you have two functions of time, we have to convolve them, okay, which is what would happen if it were a discrete time system, where one function represents the transfer function, one represents the input, the output with the convolution. In this case, we can simply take the product of the transforms, and that makes life much easier. Okay, I'm not going to have time to cover that anymore, so I'm going to stop, and we'll continue with the Z transform. Now, your homework, so we had last times, which I didn't collect, so I'll pick up that now. And then the second part of this homework, just keep it, and I'll pick it up on Friday, and hopefully you can predict my teaching better next time.